In the previous video, we looked at a morphological matrix of phylogenetic data published by Huttenlocher and colleagues in 2018, and they focused on morphological data that you can sample for fossils. And we took a very small subset of the living data that I'm highlighting right now from the Huttenlocher et al. Dataset, and we combined it with sequence data, with DNA sequences from the alignment published in a paper by Upham and colleagues in 2019, and that's what I'm highlighting now. Of course, Upham et al. 2019 didn't sample these two fossils, Myelestes and Pucadelphes, and that's why they're completely represented here by these strings of question marks. And what I thought I'd do in this video is give you a little bit more information about some of the formatting issues and tricks about getting a combined data phylogeny matrix to run in PAUP. And I also thought I'd tell you how to get that same matrix to run in TNT. And in some cases that's very easy because TNT can read Nexus formats, although that's not its native format. So before I get started though, I want to give due credit to this really seminal program, PAUP, also known as PAUP star, phylogenetic analysis using parsimony. And the parsimony bit on PAUP is sort of a relic from its original iteration. I think the author of PAUP, David Swafford, this is his website or one of his websites where he provides information about this program. This is a very amenable program for using probabilistic methods, in particular likelihood and distance. So it's not just parsimony. Okay, but let's then get back to the matrix that we created in the last video that I just told you about. And you may recall that we got that video to run in PAUP, and here's this file, right, that we created and just using a text file. I drag it to the PAUP shortcut there, and here's the PAUP program that's working. I hit Control-R to execute the program, and I did it already before I started this video, so it's asking me if I want to reset the actual data file. I click on yes, and so here we go. And this already it's a very this program gives you helpful feedback as it's being run. So for example, it's read it in DNA format, but it's also identified the character states that we told it, namely 0 to 5 plus the A, C, G, and T there. It's telling us that the missing data is identified by a question mark. It's telling us that gaps are identified by these dashes, and then it's also giving us a bunch of these equate macros, right? And the only one that we actually told it to equate was the number sign. And this is, in some cases, you might want to use a different symbol for your morphology matrix to represent an inapplicable character state. The equate macro, the only one we told it was this one, number sign equals question mark, and sure enough, that's here. It tells us equate macros in effect, but it also tells us a whole bunch of other equate macros. And this is because we have told PAUP that our data type is DNA. And along with it, it automatically is a number of character states or representations of character states shown to you here. So that's a very helpful example. If you want to read more about that, here's the PAUP manual. You just click on that. And this is the acronym representing these character state symbols, IUPAC. And sure enough, in the PAUP manual, it tells you if data type is set to DNA. Then here are all these character state symbols that you've just seen on the PAUP window. Okay, so now that it's successfully read in this, tell you what, let me just clear the display buffer, and I'll just run it again so it looks a little neater. Now that we've run our combined morphology molecules data set, we've got it to execute in PAUP. What do we do now? Well, it's such a small matrix, and you'll probably never actually use BNB as a command. So you can see I've just typed here in this command line section BNB, that means branch and bound. You're guaranteed to find the shortest trees. I hit return, and because there's so few taxa, there's just 9 taxa, it immediately finds the single tree at 7,076 characters, right? And this is all just using parsimony analysis criteria set to parsimony. You know, it's not really informative. I mean, I can show you the tree here, single tree. So show tree, I type in this little command line interface, and there it is. It's shown as rooted. This is arbitrarily rooted on Macropus because that's the first taxon that's in the matrix. And of course I can change that if I wanted to. All I have to do here is type outgroup, why don't we say myelestes, and it's changed the outgroup. I just showed the tree again. You don't have to redo the search, you just type show tree again, and there it is with the South American fossil comprising the outgroup. Some of the information that PAUP gives you when it outputs or when you execute a program is really useful. So for example, here it's telling you the number of total characters, 39,637. It's telling you that all changes for every one of these character states within each character all the changes are the same cost, so they're unordered or non-additive. They all have equal weight. It's telling you how many characters are constant, how many are parsimony uninformative. It's telling you what the gap treatment is. Maybe I'll make another video later on with details about these variables here. That's really useful to have. But before I do that, there are a couple other things that I thought maybe you would find useful. So for example, maybe I'd like to be able to delete or restore a certain category of taxon. The obvious example of that are fossils and living. So in that case in PAUP, there's a very intuitive command called sets. So I type here begin sets ending with a semicolon. That's a general modus operandi in PAUP. Just for ease of reference, I add a tab, and then my first set is going to be a set of taxa. So that's a tax set, and I'll just call it fossils. And there's an equal sign, and the last two taxas start numbering from 1. So 1 to 7 are the living taxa, 8 and 9 are the fossils. So I can just say taxa 8 and 9 are fossils. I can also write out the taxon names, but numbers are shorter, so I'll stick with that. Here's another set, tax set extant. Those are the living species, and those are 1 to 7. So then I want to end that block, and maybe I want to do something similar, but this time with characters and not taxa. So here I can say, I can just go back into my sets and say, this time a char set, character set, char set morph, and morphology are, as I've written here, the first 538 characters. You may remember we did ourselves a favor by putting the little comment just before the morphological part of the matrix, which of course is interleaved. So the first 538 are morphological characters, so that obviously is going to be 1 to 538. And then the next one is char set, char set DNA equals 539, right? Just numbering from 1 to the end of the file, which is 39637, 39637, right? I just copied it from the number of characters in the file header. And let's execute this and see if it works. So I've made some changes. So it's asking me, do I want to save? And I do want to save. So I reset the active data file. And I didn't make any typos. I mean, sometimes that happens. It accepted it. So let's just see if this works. Now, if I want to delete, say, fossils, I don't have to redo another matrix. All I do is make this command, delete fossils, that I just typed there. And there it is. 2 taxa deleted. I can do my, and this time, the more typical kind of search that you would use is a heuristic search, and that's just H search. And you can specify some items like the addition sequence is random, and let's do just 100 reps, 100 replicates equals 100, and it does this really quickly. And in every replication, it's hit the optimal tree 100 times. Again, this is a really easy data set. And so, but remember, I just excluded the fossils. So if I now show tree, you only see these 7 living taxa. Now let's see what happens if I do the analysis without any of the DNA. So in this case, rather than delete, right, the previous command that I gave it there was delete fossils. This time I don't want to delete anything. For characters, you want to exclude, and then the name of the character set is DNA, so I exclude DNA, and here it's told me that it's deleted 39,099 characters, and of course, sure enough, that's the number of sites that I pasted in here from Upham and et al. And so if I now do that same search, you can use these arrows just to scroll through the previous commands that you ran. And I thought, there it is. Heuristic search, add sequence random, nrep equals 100. And it's also found it really quickly, but this time there are two shortest trees. So, you know, I could, if I do show tree, it will only tell me one of the two trees. So either you can do show tree 1 and 2. That's 1. Here's the tree number 2. So there's a subtle difference in the position of, let's see now, within this Acrobates pseudocheiros petaroides clade. You can see that at a glance by making a consensus con tree, and it defaults to a strict consensus, and there you can see that group there's a polytomy, right? So a single node connected by 3 branches. Okay, so now what I thought I'd do is get the same data matrix, combined morphology molecular data matrix, to run in TNT. And this is rather less intuitive. It takes quite a bit of trial and error. So hence this video, so that you can avoid some of the trials and errors that I had to go through. And while TNT doesn't use Nexus as its native format, it can read Nexus files. Unfortunately for this file, you do have to make a few changes. Let me give credit first to the authors of TNT. This is first came out almost 20 years ago now by Pablo Golubov, James Ferris, and Kevin Nixon. The website here is maintained by, I believe it's the group of Pablo Golubov in Tucumán in Argentina, and it's a really effective phylogeny program. And for many, not all, but many problems in phylogenetic inference, in particular parsimony, it's really, really fast. It's probably the fastest option that you will have for complicated data sets to run using parsimony. So here's the matrix that by now, if you've been watching these videos, you're familiar with. And if I just naively say I want to try running this in TNT, you could give it a try. Here it is, combined next. That's the one that I've been showing you. And if here's my command line version of TNT. I don't really use the GUI, the graphic user interface, but the command line does everything that the GUI does, and is, I think, easier to use. All you have to do to start out with is type proc, which is an abbreviation, I think, for procedure. You don't need to write it the whole world. So proc combine.next and see what happens. And you get an error. Here it is. So there's something else we have to worry about here. And this is what I want to show you. Let's start with the morphology only in TNT and just leave the Nexus format and see if that works. So I'm going to delete all of the DNA part, which means that I delete the interleave bit. It also means I have to change the number of characters to only the 538 morphological characters, which is very easy. So there's one other change I need to make, which is to not have this a DNA matrix. It has to be standard to get TNT to read a Nexus format. It doesn't like mixing a DNA format with this extra set of character state symbols that you can use in PAUP to use a combined DNA morphology dataset. TNT doesn't like that. TNT has its own format that I'll show you in a minute. In any event, I've just changed it now, right? Data type away from DNA to standard. I'll save it, and now I'm just going to try and execute it again, and there it is. It works. So the whole point of the exercise, though, is to be able to read into phylogeny programs like PAUP and TNT a combined morphology DNA data set. So we don't want to delete all the DNA like we did a moment ago. We want to keep it. So let's then use the native TNT format. And that is going to require a bit more effort here on our part. So what I'm going to do is go back to that combined Next file that did work in PAUP, and I'm just going to change this to native TNT format. So in TNT, you need a few initial commands in this format. So the first command that you'll find useful is maxram. It's not a lot of taxa, but there are almost 40,000 characters. So if I just up the RAM that is made available to TNT to 99 with this command. I think it should work. And then xread, the number of characters, the number of taxa, ampersand num representing the morphology data here, and then ampersand DNA representing the DNA. And then you have to close the data file with this proc / semicolon. There's actually one more change, but I want to show you the error before I tell you what that change is. So if I try to do this now, proc combine TNT, I get another error, and you see it's because there is a polymorphism here, right? So there's that curly bracket. So now what I have to do is change all the curly brackets, and there it is. I think that's the only one. I've just tried to find it multiple times. So all I have to do now is change this to a square bracket, and remember the close one, the close it as well. I mean, you could do a global search and replace, because usually you'll find multiple instances of this sort of thing. But I just found the one. So I've saved it, and now I'm going to go back to TNT, procedure, proc combine TNT, and there it is. I have the data set, 9 taxa, almost 40,000 characters, and it's sort of defaulting to 16 states. There are a couple more changes here that are worth pointing out. With TNT, you have to tell it not to treat gaps as 5th character state. So I have a little cheat sheet here of a file that works, so I have to use this command, end states, no gaps. So end states, no gaps. So that's one. I'm going to save it. And then this, you'll notice here, it requires 45 megs. I mean, I gave it megabytes of data. I gave it 99, so it's still within that range. But you can, I think you can make the memory requirements even lower, because there aren't more than 8 states here. So if I just tell it end states 8, I think that will work as well. And let's see if the memory requirement goes down. Yeah, it does. So here I've just executed it again, and instead of 45 megabytes, it has 14 megabytes. You know, this has the advantage if you want to run multiple instances of TNT, which is really useful, actually. I can keep hitting that executable as often as you want. Open multiple windows of this thing. This is really one of the big advantages of TNT. And within each of these windows, I can have my own little phylogeny program running. So imagine running a big batch file and dividing that up, and it's almost like running it on a cluster. I mean, that's a bit of an exaggeration, but you can run multiple analyses simultaneously and get results that much faster. So the very last thing I want to tell you about the functionality in TNT is basically the TNT equivalent of defining a taxon set or a character set. And this is what you have to do. The commands are not quite as intuitive as in the Nexus format, but they work. And if you want to define a taxon set, the command you need to add at the end of your data file are a group, and you need the equal sign, start at the number 0, call this group the name you want to call it. So the taxon set defined as fossils consists of taxa 7 and 8. And now this is another somewhat counterintuitive aspect of TNT, in that in some of the functionality you start numbering at 0, not 1. So there are 9 taxa here, but in this case they are taxa 0 to 8, not 1 to 9. Right? So the last 2 taxa, Myolestes and Pucadelphes, the 2 fossils, are 7 and 8, not 8 and 9. Similarly, the first 7 taxa, these 7 extant marsupials, are 0 through 6, not 1 through 7. With morphology, it's the same, right? Even though you have 39,637 characters, combined morphology plus DNA, the first 538 of which are morphology, you start in these taxon and character sets numbering at 0, not 1, so 538 characters are represented by 0 to 537. Similarly, the last block consists of all the DNA, and that starts at 538, and it goes to the end, which is 39,636, not 637, because this is numbering from 1, whereas in this taxon and character set, you want to start numbering from 0. So let's, I've already saved that. Let's execute TNT and make sure this works. Proc combine.tnt, it works, right? So the very last thing, I guess, is when you want to exclude taxa or characters, in the case of taxa, then the command is tax code minus, and then you need a curly bracket, and then you just use one of these terms, fossils, ended with a semicolon, and there you have it, 7 active, 2 inactive. With excluding character data, it's a little, the command is not intuitive. You need CC plus the, I think it's the end bracket, the end square bracket, followed by a curly bracket with the name of the type of character you want to exclude. Let's say DNA for now, closing the curly bracket, ending with a semicolon there, and it doesn't tell you right away, but if you do CC colon semicolon, sorry, CC colon, CC semicolon, it'll go through the whole list of characteristics, and you'll see wherever you have that right bracket is a character that's excluded, and whenever you have these left brackets up here, right, these are all the morphology characters, and these are included, right? So some of those are left brackets, others are right brackets. So anyways, there you go. Once you get over the somewhat counterintuitive commands, otherwise I think you'll find TNT is a very effective and fast program for executing parsimony phylogenetic searches. Thanks for listening.